Good afternoon all and welcome you all for this session. So today's agenda will be our HOD Dr. K. Balasubramanian sir will inaugural the international webinar session followed by the department college video for few minutes for 4 minutes. Then there will be an introduction about our chief guest. Then the session will be given to the hand of our chief guest. Then at last, for 10 minutes, question and answer session will be there. You can post your questions in the chat box so that our coordinators will read out the questions to the speaker and you can get the answers. Those who are in YouTube live session, you can post your questions in the YouTube live chat box. Then the questions will be read out either by any one of the coordinator to the speakers. Then you can get the answers. Sri sir, live. I think you have gone into live. Correcta?
Okay.
Sri sir.
I on my video.
Yes sir. Yes sir. I
Okay.
have shared. I have shared the YouTube link to in your WhatsApp number, sir.
Okay.
So
Okay. Good.
yes, after the question and answer session, we will post the feedback form for the participants to be filled. So after getting the feedbacks, you will be receiving your certificates by end of this week.
Okay.
These certificates by end of this week. Yes,
Okay.
now I request Dr. K. Balasubramanian sir to inaugurate the international webinar session.
Okay. Sure.
Should we start?
Yes sir, yes sir, yes sir, we are ready, sir.
Okay.
Good afternoon to everyone. This is Dr. Balasubramanian, Head of Department of Mechanical Engineering of Meenakshi Sundarajan Engineering College, Chennai. We welcome Professor Yukoba from University of Science Malaysia, School of Mechanical Engineering from Malaysia for this particular webinar today. I just briefly inform you about our campus. Meenakshi Sundarajan Engineering College is started in the year 2002 by Professor K.R. Sundarajan, an eminent educationalist during that time. And it is a brainchild of him from Indian Institute of Engineering Technology, which is started somewhere around 50s. From there, his aim is only to give important educations to all the backward class, that is economically backward community. That is how the IIET started, which is equivalent to BE degree those days, which is equal to AMIE, which is sectional examinations during that time. Now, this section is very useful to us by Dr. Yokowa because we constantly pursuing with University of Malaysia, which is once again the brainchild of our director, Professor K. Srikanth, who is our director, and Dr. K.S. Bhavai is our secretary. Under Bhavai Madam's support, we are now conducting this webinar, and we welcome once again Professor Ukova for this particular section. I will hand over the mic to my colleague, Vadivel.
Okay. Thanks, Prof. Bala. Nice to know you. Although that we haven't meet face to face, but it's very kind of you from the engineering college to invite me to give share something about the superhydrophobics. So is it my turn to share to start? Shall I start or?
Yes, sir. We have 4 minutes video about our college, sir. Sridhar, sir, I
Okay.
request Sridhar, sir, to play the video.
Yes, sir. Thank
Okay,
you, sir.
sure.
Okay. Um, sir,
Vadivel,
little
sir.
more, sir.
Vadivel,
I
sir.
request,
Vad-
yes, sir. I request you to make Sridhar as a host for a few minutes to play a college video in Zoom app.
Okay. Okay.
Yes. You have to go to the participant, sir. You have to go to the participant and click K Sridhar.
Okay. Is it this one?
No, sir. No, it is not. Sridhar, K Sridhar.
Okay, yeah. Then make host.
Make host. Yes.
Okay, sure.
Yes, sir. Sridhar, sir, you can play in Zoom app, sir.
Oh yeah, thank you.
Thank you, Sridhar sir, for the wonderful video of our department from Meenakshi Engineering College.
Thank you,
Now it's
sir.
time to introduce. Now it's time to introduce our chief guest. It's a pleasure and honor to have Dr. Yukova from University Science of Malaysia. It's my honor to welcome you, sir, and introduce you in this international webinar session. Dr. Yukova received his Bachelor of Engineering honors in Aerospace Engineering from University Science Malaysia in 2008, Masters of Science degree from the same university in 2011, and he obtained his PhD in the field of fluid mechanics from National University of Singapore (NUS) in 2016. He is graduated member of Board of Engineer Malaysia, and currently he is a lecturer in School of Mechanical Engineering, University Science Malaysia. His current research areas are focused in thermal management, in microfluidics, then applications, micro mixing applications, flow stability, and surface mount technology. He is a recipient of fellowship RLKA University Science Malaysia, USM Fellowship, and USM Graduate Teaching Assistants. He was previously attached as a visiting scholar to the project of miniature UAV development in National University of Singapore UNUS in 2011. He also involved in project in investigating the potential of suspended liquid gas interface for heat transfer application in channels under turbulent flow. He has published various research papers. He has good citations in Google Scholars. Today, it's a pleasure to have you, sir, and I welcome on behalf of our Meenakshi Engineering College and Department of Mechanical Engineering to you, sir. Now, the session is yours, sir.
Okay.
Thank you, sir.
Thank
Thank
you.
you.
Yeah, it's a great pleasure to have me to share a bit on my research project, and I'll be on behalf of my university to share about these projects. So, can I share my screen? Is
Ah,
it
yes, sir.
possible?
Yes, sir.
Okay.
Yes.
Okay.
Now you can share, sir.
Okay, sure. Okay. I'm really thankful that I have this kind of opportunity to share with our foreign counterpart, especially those from India. Uh, this for this session, I'll share about the superhydrophobic surface. This topic have been done since my PhD in NUS. So just because of this audience that we have are mostly student, so I'll try to keep it as basic as possible, just to talk about the science and mechanical, but I'll add in some elements of the mathematical and also some simulation part because I did a lot on that. But so myself, my name is Yu Kok Hua, so you can call me Dr. Yu. So I've been attached with the University Science Malaysia 2017. There, okay. So a warm greeting from University Science Malaysia. Just if you are wondering where USM is really at, is at the peninsula of Malaysia, so about north of the Malaysia. So you can see over here is that the USM in Penang. Penang is actually a state, a small state that we have in Malaysia, and we have separated campus within Malaysia that we have for USM. Actually, we have 4 campus, 2 or 3 are in Penang. So we have the main campus is actually in the main island. So Anjing campus is actually in the mainland. So this one is the Penang state. So to connect between these two parts, there's two iconic bridge that we have. So just travel is quite quick. Just travel between like 15 to 20 minutes, you'll get to the main island, and there's plenty of attraction in Penang itself. So there's plenty of attraction in Penang itself. There's plenty of tourists. Let me try briefly to introduce Penang. And many people did come to Penang just actually to see the wall painting. So one of the famous wall painting that we have is the kids on the bicycle. So this painting actually attract a lot of tourists from around the world. If you come to Penang and you haven't go to this place, it doesn't consider that you have come to Penang. So that's the importance of this kind of painting. So besides that, we have a lot of other attraction like the Buddhist temple, the Kongta Tower, and you can go to the Penang Hill. So when you have time, you can go to Penang Hill, and that's the scene from the hill itself is quite nice, especially in the night time. So if you have the opportunity to come to Penang, probably you can let me know. I'll try to give you a tour inside Penang. And a little bit about USM. So USM is quite a nice campus. I attached a nice photo of my campus, and below part is the convocation of the USM that we have in USM. Probably not this year. Probably we have it probably next year. So USM is actually established in 1969. We celebrate the 50th anniversary last year. So this year is 51. So USM can be considered as the second oldest university in Malaysia after UM. So there's a total of 24 schools with multiple disciplines. So one of them is mechanical engineering. So approximately we have at one time the student is around 5K at one time. So this one include the bachelor degree and also the postgrad degree. And USM is actually recognized globally. So in QS ranking, actually we are top 200 this year. So next year, I think the ranking released is much more higher than this year. Okay. So a little bit about the school of mechanical engineering. So this school is one of the school in engineering campus. We have the civil school, we have aerospace, we have electrical and electronics, we have material, we have chemical. So mechanical school is quite good. Actually, we are top 100 in a few years. So this one is just a simple brochure of the our school. Okay, how do I get to know to your college? Is that actually there's one student who came to USM to do his research internship, and his name is Prakash. He actually come in December, and within 2 months we are able to do some project about the superhydrophobics, some project about the safety. So from there, he learned quite fast and can master on the project itself. It's quite quick, and he's already graduated, and now I believe in United States. So this photo are on his last day. So actually we accidentally wear the same color shirt and with the same pattern. So it's good for him. Okay, so this one is just a basic content for this webinar. So I'll try to go through some basic introduction on the superhydrophobic surface. Then I'll go through some importance or some topics of application for superhydrophobics. Okay. Okay, just to wonder that what is superhydrophobic, and often what people call it is an water repellent surface. So this water repellent surface is that it become our interest in the scientific community from observing the nature. So when the researcher observe the nature, especially on the plant surface, So this one is on the lotus leaf. So there is water repellent properties on the lotus leaf. And if we go in micron size or small scale, you can see that actually there's protrusion, small protrusion that you can see under the scope. So this one is reported by Sun in 2008. So if you see when there's water inside on top of the lotus leaf, so you see that the water itself gel together. So it gel together, it doesn't really wet the leaf itself. The leaf itself is actually dry. So you can see that the water itself is rolling over the leaf, gelling together, sticking together. It doesn't really wet the surface of the leaf. And this type of surface is called water repellent or hydrophobic. Okay, if we take the same thing and we use water and wet the paper, so the paper itself will get wet. So this one is typically known, but we can have hydrophobic coating on a paper. So probably we watch what will happen to this paper. Okay, so this one is ordinary papers. If we have water on top of it, it will sure wet the paper. Okay, if let's say that the paper itself is being coated with hydrophobic, so when it coated with hydrophobic, the water itself won't wet the papers. So this one is the one who that wetted. So typical one. This one with the treated one. So when we have treated paper, although this one is a paper, so this one is just a normal paper, just treated or coated with the hydrophobic properties, and the water dropping on top of the paper will form only droplet. So you form only droplet, and this droplet will stick to each other, but not to wet the paper itself. So this one is quite an interesting phenomenon that uh, give attention to a lot of researcher to investigate what's the application that we can do with this kind of the condition. So before that, we have to know the properties or the fundamentals of the surface itself. So a basic drop of liquid on top of the surface. So this one is the balance in formation of the liquids. So what we have over here, the gamma itself, is the surface tension coefficient. For SL is for solid liquid, Lg is for liquid gas, and Sg is for solid gas. So the balance itself will form the contact angle as phi. So the contact angle is basically dependent on the surface tension. So there's a different degree of wetting. So what we can see over here is that if we have total wetting, so the phi or the contact angle is 0 degree, partial wetting we have 0 until 180 degree, and we have non-wetting to be 180 degree. So that is the condition that we have. And when we have roughness, so this one is a structure roughness. So when we have structure roughness, something like this, we have width, we have groove, we have grid, and we have groove. So there's two conditions that for the droplet to form. So one condition is called the fully wetting, it's also called the Wenzel state, and another one is called partial wetting or the Casey state. So the B one is called the hydrophobic with the hydrophobic coating. So if there is a small surface roughness and the hydrophobic coating, the sealant surface is often called as the superhydrophobic surface, because with that small roughness, the contact angle itself is much more larger as compared to a smooth surface. Okay, so we can have a texture surface or we can have a random surface. If we have texture surface,
Sir,
that
sir,
yes,
hello, sir. Excuse me, sir.
yes, yes.
Sir, can you just increase your volume in the laptop, sir? Some participants are saying that your volume is very low.
Okay. Uh, Probably I close my video and put it closer. Okay. Okay. Is it clear now?
Yes, sir. Okay,
Clearer?
sir.
Okay.
Yes, yes.
Okay. Okay. If we have a texture surface and we have that texture surface, there's a lot of combination of or arrangement that we can do on the surface. For example, if we have the flow from left hand side to the right hand side, so we can have the groove and rib to be aligned in longitudinal, meaning to say that we can have it at parallel. So we can have the same combination of structure in the transverse. So it will be called as the transverse groove. And we can have also square holes and square holes. Square holes is that we have a hole that is in the form or the shape of holes, and holes you have protrusion in the shape of a square. Okay. Okay, so this one is in the experimental work. So in the experimental work, what we can have protrusion, we can have holes, we can have ribs and groove. So this one is been fabricated in 1999. So this one is not really exact square, but there's protrusion and holes that can be made. But that kind of size is in small micron size. So there's a list of application for superhydrophobic surface. So we have mainly what we have is that on the reducing the flow friction in the internal flow, thermal management, lab on a chip, self-cleaning, condensation, waterproof surface. So some of the application I'll go through in details because it's quite related to my research project. Some I'll show you the general application. Okay. So this one, beside that, this water repellent surface that we can see on nature, we can have it fabricated on the surface. So this surface is being treated. When you drop a liquid water on top, it won't wet the surface. It will form just a droplet. Okay, so if you are learning about fluid mechanics and there's a limitation that you know about fluid mechanics in internal flow, so to have that fluid to pump from one end to the other end, you need some pumping power, meaning to say that you need a difference in pressure or you need some pressure difference. So when we have circular tube, the delta P itself is inversely proportional with R to power 4. And for non-circular channel, we can have it as a square, rectangle, triangle, and that also inversely proportional to hydraulic diameter to power 4. So in reality is that if we have a smaller tube or channel, and the pumping power will increase tremendously. So for example here is that if we have tube with radius R, capital R, let's say the pumping power itself to pump from one end to other end is delta P. If we reduce the size of the tube by half, so it will become 0.5 R, the pumping power to pump in the same distance will increase by 16 times. So that will be tremendous. So you can imagine that in microfluidics, when channel of tube are very very small, so you have problem in pumping the fluid. The fluid won't even flow properly. So that is a kind of limitation that we have, and superhydrophobic surface try to address that. And if we see the velocity profile that we have on this schematic diagram, so we can see on no slip condition and slip condition, we have solid on the bottom, fluid on the top. So we can have two types of condition. One condition, no slip, is applied normally on smooth surface. When the solid itself stop moving, the fluid close to the solid on the solid surface won't move as well. That's why the velocity of that part is always zero. So we have another condition for slip. And this slip is that if you can observe it on the surface of the solid, we can see that there's movement of fluid. So there's a certain amount that's not zero. So that certain amount not zero, can say that that condition itself to be slip condition. So normally researcher like to quantify this type of amount of slip length. So when you have the amount of slip length, that slip length if larger dependent on the velocity profile. Velocity profile and okay. So there's benefit on the application. And so the application itself is that more flow
Sir,
using
excuse me, sir.
yeah.
Yes. Participant, one of the participants, Jayakar, please put off your mic. Participants, please see to that. Please put off your mic when the speaker is on. Thank you. Thank you.
Okay. Okay.
Thank you, sir.
Thanks.
You can. Yes, sir.
Okay. Okay. So I'll continue. So for this type of condition is that people like to quantify the slip velocity in terms of slip length. So this length itself is quantified based on the velocity gradient and also the distance that we have zero velocity. So this distance is always positive is if we have slip velocity to be positive. So the benefit of this slip is that when we have more flow flowing close to the wall, so we have more flow in the same pumping power. And also with that, we have less friction or drag. Okay. Okay, so there's a lot of existing study that been done on this topic. So mainly on the flow friction reduction. It started with Philip in 1972. So Philip did a good job, try to come up with analytical study, quantify the slip length respect to the condition that we have. Lauger and Stone actually extend that study to cover longitudinal and transverse group. So there are also some numerical study and also experimental study. So mainly what we have when people use hydrophobic or slip surface, they always reported that there's positive effective slip length when we have that or we pump water inside channel or tube. Okay, so this is the first one. When we try to investigate or to study about the fully developed channel flow, this one is the governing equation. Left hand side is the anyone else? So anyone else on your mic? Okay. Okay, so left hand side, if you can see, is that the schematic diagram for a period of the groove grid period unit. So on top, you have superhydrophobic, on the bottom, you have superhydrophobic. How you want to model it, you just model a period of the flow. So a period of the flow is sufficient that you assume the flow besides are all periodic. So this one, what we have is that we have on this superhydrophobic surface, when we try to pump water inside it, there's always gas that we trap. There's always gas that we trap when there is cavity. So if there's cavity on the surface itself, there will be gas. And these are the main ingredients that they have to reduce the flow friction. So you can see over here, for solid liquid interface, you have shear stress. And for the liquid gas interface, you have less friction. So with that less friction, in total you reduce the pumping power. So this just a general modeling for superhydrophobic study. So assumption that we have is that for this study, the longitudinal superhydrophobic groove are applied on both walls. So the flow itself is on the plane of the schematics. So we also can assume that the laminar, steady, compressible, and flow itself is driven by the pressure gradient. So Cassie state, and also the assumption that the contact line is pinned at the sharp corner. So also that we assume the component V and W velocity are zero. We are just concerned in the axial flow. Okay. Okay. So these are the schematic by means. So uh, I'll try to share to you the trick that we do on modeling. So how that we model the problem. And we know that there's air cavity or cavity during on the surface. So inside this cavity is actually there's gas or vapor. So when we have flow, this one is for transverse group. So the flow will flow from left hand side to right hand side. So when we have that flow and we have cavity, so the flow will flow from left to right. So on the surface, on the interface between the liquid and the gas, there's also some gas flow from left to right. So close to this interface, you have left to right, bottom to that surface, you have right to left. So you create a circulation. So that circulation just a movement of air inside the cavity that not going anywhere. So on that interface, actually there's small amount of stress that's been reported. But to simplify your simulation part, you can neglect that and assume it to be shear free. So if you use that shear free boundary condition, you can save you a lot of trouble. So what you try to model itself is only the fluid domain, not both. So both meaning to say that you have to simulate the liquid and also the gas. But if you do simplification on the liquid gas interface, you can just simulate the liquid domain. Okay. So this one is the sorry. Okay. So this one is the parameter that we always investigate. So it's L. L is the sizing of the periodic unit. So you have the small l meaning to say that the size of the microstructure is small, and large L is saying that the size of the microstructure itself is bigger or wider. Shear free fraction itself or area interface fraction is saying that how big the size been occupied by the gas. So small delta, we have a narrow gap. Big delta, we have a bigger gap. Okay, so these are the simulation that we have done on different parameter. Left hand side is for intermediate L, which is L equals 0.5. Right hand side is L equals 2. So you can see that actually there's a velocity field that changing when we have that kind of different parameters. What we can see over here is that if we have more gas area that being occupied by the liquid, so what we have is that more fluid will flow. You see the blue color is more higher velocity, and those with red color are the low velocity. So if you have more solid surface interface, then flow gets slower. If we have much more gas area interface, then the flow of liquid will be faster. Okay. So this one is the effect of the liquid gas interface curvature. So in reality is that the liquid gas interface is not always flat. So it also occupy in the form or shape of the convex and concave. So we have convex and concave, and that also influence the flow. So if we have concave, then we'll have some blockage on the flow. If we have convex, then the flow is much more smoother. Okay. So besides just study on the just longitudinal groove, we can also study multiple pattern of the surface. We can have it longitudinal, transverse, square hole, square post. This one has been done by Cheng, 2009. So this one is just to assess the effect of the fluid inertia on the effective slip behavior and to compare the friction reduction capability of the different pattern. So the result is that what we can see on the blue color is the longitudinal groove. Left hand side is for gas area fraction of 0.5. Right hand side is gas area fraction for 0.95. For 0.5 is that the area being occupied by the gas is half. Another half is being occupied by the solid. 0.95 is that the area being occupied by the gas is 95%. The area being occupied by the solid is 5%. You can imagine that you have a narrow pin protrusion. So that protrusion occupied like 5%. The rest is all occupied by trapped gas. Okay. So from that findings that reported by Cheng is that longitudinal groove have a higher enhancement respect to 0.5 and 0.95. And what we have the worst is the transverse groove. Although that all surface or all pattern show positive enhancement, but minimum enhancement for transverse and maximum enhancement for longitudinal. So the enhancement also grow with larger L. You can see that it's going upward. Okay, the reason is that for longitudinal groove, when we have flow, so in contact with the solid surface, there always will be boundary layer. So longitudinal groove is that you have left hand side, right hand side, have solid surface, then you form the longitudinal groove. In the middle, if you have the fluid particle will just flowing non-stop until it reach a fully developed values. So it won't be disturbed at the middle. So for transverse groove is the opposite. So if we have transverse groove, you have left hand side, middle, and right hand side all will have boundary layer. So when we have fluid in contact with the solid, the fluid itself will decelerate. And at some times you stop. So after that, you're in contact with the liquid gas interface, and the fluid molecules will start to accelerate until it reach encounter another solid surface. Then the boundary layer will start. The fluid itself will decelerate. So itself, for the transverse groove itself, we have this kind of method. It's the flow itself will stop, then start to flow again, then stop, and start to flow again, then that disturb the enhancement. So this one is important. So besides what we do for channel flow, we also can do it for circular tube. So doing for circular tube, the coordinate system itself is not the same, but it's quite similar. So this one is the result. Left hand side, we assume that the liquid gas interface to be flat. So flat in this case is that it don't have any curvature. So this one only vary on the gas area fraction. So if the fraction increasing, the flow itself there's more flow. If you have constant pumping power. Right hand side is that if we have a constant pattern and a constant size, and we have a different curvature from concave, convex to concave. So we have different velocity field as well. Okay, besides doing on the fully developed flow, fully developed flow actually meaning to say that the flow itself is fully developed. There's no entrance effect. So we also can study the entrance effect. So when the flow is at the entrance, so the inlet flow itself, if you can see the velocity profile on your left hand side, you can see that uniform velocity profile initially, that when it go into the pipe or inside the tube, the velocity profile will start to develop until the profile itself remain the same throughout the tube or pipe. So during the period that the profile itself is the same, we call it as the fully developed region. And before that, we call it as the hydrodynamic entrance region. There's some existing work that been done for the Newtonian fluid in entrance flow. So the work by this is quite impressive. So there's a correlation to predict the length that needed by the fluid in order to reach the fully developed flow. So this correlation is quite useful. And also there's channel flow with wall slippage that been done by Farash and Mojit. So, but what been done inside the existing work is that the fluid and the slip condition being modeled as arbitrary. So arbitrary means to say that the slip itself at different position in the width, span-wise, and also the axial direction are all the same. So no one has actually done on the texture. So no one has done on the texture surface. This one for the tip, the lower figure is for the tip. So no one has done on the texture. So this one is a research activity that I took to investigate on this flow condition. So we have texture flow, texture surface, we have grid, then we have groove, then alternating. So this one is the modeling of the problem. So the flow is actually from left to right. So on the surface, top and bottom, we have the superhydrophobic. So superhydrophobic, but we only consider simulating the fluid, the liquid domain itself only. So right hand side, you can see the governing equation. Governing equation is quite simple because this one is only 2 dimension. So assumption is just a normal assumption. We have incompressible, steady, laminar, and Newtonian. So the result that we have is that when we have superhydrophobic, the flow profile itself changes. The shape itself doesn't change. The black line is for the smooth wall. The red one and the blue one is for superhydrophobic with different parameter. So what we can see over here is that the profile itself at the center line, velocity profile at the center line itself is reducing the magnitude or the maximum. So for this case is that when we have the same mass flow rate or volume flow rate, if we allow more fluid to flow at the surface, so lesser flow will be at the center. So for entrance length itself, also it influences the entrance length. So entrance length will get much more longer if we have superhydrophobic. So this one increase with the L. So this one is respect to Reynolds number, the length that requires to reach fully developed flow, and respect to Reynolds number. You can see that if we have larger gas area fraction, the distance itself will be much more higher. Okay. Next, beside doing on the Newtonian fluid, we can do also for the non-Newtonian fluid. So for non-Newtonian fluid, we have like blood, okay, and it can be categorized as shear thickening and shear thinning. Blood itself is shear thinning. So Newtonian fluid is that the viscosity will remain the same with respect to the shear rate. Non-Newtonian fluid is that the viscosity itself is not constant. It's either increasing or decreasing with the shear rate. Okay, so one way of modeling the non-Newtonian fluid is that we can use the power law fluid modeling. So when we have that, we have a power law index, that's n. So when n equals 1, it represents the Newtonian fluid, and lesser than 1 will become shear thickening, and larger than 1 will become shear thickening. Okay, so when we have different of n, so we have a different flow profile. So you can see over here that for shear thickening, the profile at the center or the bulk is much more flattened as compared to Newtonian shear thickening. So the existing study that we have are mainly on the smooth surface, and there's people that started to do on textures, superhydrophobic surface, but none of them have considered the power law index and Reynolds number. So it's a research opportunity that I have to do on this texture surface, superhydrophobic surface. So the result is that this one is the Gaussian equation. So Gaussian equation is just quite simple Gaussian equation, just 2D, but we have to incorporate the power law modeling. So this power law modeling involved with the viscous stress. So viscous stress is dependent on eta. If you can see that viscous stress has 5 of them, all are dependent on eta. So this eta is actually a power law generalized Newtonian function. So this one must be incorporated. The result itself, if we can see that if we have different n equals 0.5, 1, and 1.5, profile itself, almost the same, magnitude are different. So if we can see for n equals 1.5, the magnitude at the center of the flow. So this one is actually plotting for half of the channel or half of the pipe. So bottom part is actually the center line. So we can see that higher flow will flow for n equals 1.5. Okay, in terms of radial profile, what we can see is that so we have a different position starting from z over d equals 0, that one at the entrance, and we have multiple locations until we reach the fully developed region. So we can see that the profile itself for n equals 0.5, the maximum itself is much more lower than 1.5. If you see the maximum U over U average. For shear thickening fluid, we can see that the maximum velocity itself at the R over D equals 0, you can see that it reached much more than 2. So the profile itself is not same if we have different fluid. And this one is the satellite profile. So satellite profile, if we have smooth surface, so superhydrophobic, so the SHS is actually short form of the superhydrophobic surface. So we can see that a lower flow rate at the bulk flow or non-Newton flow over the superhydrophobic transverse group, and the shape of the velocity profile along the satellite remain unchanged. So the profile itself will remain unchanged. Start from z equals d equals 0, that one at the inlet, then after that throughout the pipe. Okay, previously what we are talking about is just for the laminar flow. Laminar flow is that it happens when flow is being pumped at low Reynolds number. So when we have low Reynolds number, the flow itself is much more in order. So your flow in order streamline will be quite smooth. We also can do for turbulent flow. For turbulent flow, what that I did during my doctorate study is that I do turbulent flow for superhydrophobic flow surface. So this one is the governing equation that we have, just simple governing equation. So it solves the continuity momentum equation, but what we have is that we have to make it as non-dimensional. So we have superscript plus, that one is non-dimensional. What we have on top overhead bar, you can see this one x, y, and t. That one is the average. So these are the assumptions that we made, and the solver itself is called direct numerical simulation. So it doesn't really include any turbulence modeling. So there's other turbulence modeling you can do, like LES, RAMS. Okay, for turbulence modeling is that there's a concern that size of the domain. So I try to compare my size of domain with the other researcher like Martel, Turk, Park. So my size domain itself is pi 2 and 2 pi. So that is the minimum size that needed to do the turbulence flow. Because if not, then you influence the result itself, because you need a sufficient length. Grid size itself, what that I do is that I have 512 times 256 times 256. So that will become like more than 3 million. So imagine that I have 3 million element or nodes, and after that the resolution. Okay, so this one is the results. So the main satisfaction that I have while doing the turbulence flow is that when the coding or the simulation works and the result look quite beautiful. So you can see that there's perturbation, there's flow, unsteady flow, there's non-uniform velocity profile. So this one you can do that with EMS. So for the result part, if we can harvest it, can look at it, the black line itself for clean channel when we have smooth surface. And when we have superhydrophobic surface, you can see that the line itself will shift upward. So if we have larger gas area fraction, it will shift much more high, meaning to say that there's more fluid being pumped through using the same pumping power. So imagine that in terms of application, if you have this kind of amount of pumping power, you can pump this flow at this flow velocity. But if you have superhydrophobic, if you have the same pumping power, the fluid itself will flow much more faster. So this one is for turbulent flow. So besides doing turbulence flow, I also did flow stability. So for flow stability is the study in between lamina and also turbulence. So it tries to predict when it will transit from lamina to turbulence. Okay, so this one is the governing equation. So governing equation that I have and the condition. Okay, so what I have over here is that the result part look like a Y shape. So this one I try to explain to you is that we try to predict the perturbation. So all this is just the predicted perturbation. And if you see the Y part, Y axis, it has from 0 to -1. So meaning to say that if this perturbation is negative values, so that perturbation won't grow, it will die off. If this perturbation in the positive values, then it will grow. So for local stability analysis, when we do for Reynolds number 5772, you can see that there's none of them growing. What I did is that I tried to extend the study from local stability analysis to become bi-global. So using bi-global stability analysis, I can explore, and what we observe or discover is that we can have new modes of unstable eigenmodes. So you can see on the red circle are those that's unstable. So what happens is that when we have hydrophobic surface, the flow itself on the wall are not the same. So when we have solid surface, the flow itself will be lower. When we have liquid gas interface, they will much more faster. This one will create the inflection line. So tends to have perturbation. So from there itself, from the stability analysis that we do, that I did, we can see that the critical Reynolds number itself is much more lower. So it can reach until Reynolds number 1000. Okay, so that's for the flow back. For thermal management, we can do also for thermal, just include the energy equation. So just include the energy equation. So we have to solve continuity, Navier-Stokes, and the energy equation. So these are the result part. So the result for the thermal, okay, so we quantify in terms of Nusselt number. So quantify in terms of Nusselt number, what we see if we have superhydrophobic is that the Nusselt number itself is dropping. So this Nusselt number is actually the ratio of the convection over conduction, meaning to say that if we have a condition that we have flow, another one is compare that we have without flow. So let's say that Nusselt number equals 8, then 8 times enhancement. So if we have superhydrophobic surface, because we have air pockets is not good for heat transfer. So the performance for heat transfer will drop. But in terms of the overall performance, we quantify as the thermal hydraulic performance. This one, we see a lot of enhancement. So we try to get the trade-off between hydraulic and thermal. For small L, it can reach until 20%. For intermediate L, it can reach 40%. So that one is quite impressive. And this one is also for turbulent flow, but this one is for heat transfer. So heat transfer, you can see that on the solid surface is spread harder. So meaning to say that over there is high temperature. So on the bulk of the flow, there's a lot of non-uniform field. Okay. So this one on the surface of the superhydrophobic, so different delta 0.25, 0.5, and 0.75. Okay. So beside flow, beside heat transfer, superhydrophobic surface is actually good for self-cleaning. Because when we have superhydrophobic surface, when we have liquid on that surface, the liquid itself rolling quickly, much more quicker. So it can take the dirt or the foreign ingredient over the surface. So probably I show you the videos. Okay. So you can see that the water itself won't stick to the, the windshield. So if we coat it with the hydrophobic liquid. So another things besides self cleaning is that it make the surface to be waterproof. So probably I can show it to you the videos. Okay, so you can see that if we try to apply the hydrophobic coating on a cloth, shoe, so you won't get wet. So actually that's quite useful. And this one is the last one. So one of the application for the superhydrophobic surface. It's quite interesting. Okay, so uh, this one you can try and do the hidden message using the superhydrophobic or hydrophobic coating. So you just coat some words on some design on the floor, and when there's water or rainwater, so the message itself will appear, and won't have the message when there's no rain or there's no water. So that's all for my sharing, and I would like to thank the Minashi Sudara Rajan Engineering College for provide me the platform just for me to share on this topic. So Prof. Balasubramaniam, so Mr. Padival and his colleague. And okay, so I hope you can get or digest some of the important insight about this topic. It's quite an interesting topics that we have. So thank you for listening and bear with me for like 1.5 hours. So I hope you get something from this sharing. And also, if you are looking forward to come to VSM, you are really welcome. For example, that you can have research internship in USM that previously done by Prakash. So you can come. We will look forward to do some collaboration or research. It's quite good environment here. So thank you.
Good evening, sir. This is K.
Yeah.
Sridhar, uh, Assistant
Yes.
Professor Mechanical. Thank you very much, sir, for sharing your valuable time and knowledge with us. And now
Yeah.
we will go for a short question answer session.
Okay. Sure.
If the participants have raised any question, I will read it up to you so that you can answer them.
Okay.
Mr. Koa, this is Balasubramanian here.
Okay, Prof.
I
Yeah,
should thank
nice
you
to
very
hear.
much for accepting our invitation. And
Yeah, sure.
your presentation is very good for research holders. And
Yeah,
we are,
I
you may be
I
aware
try to
that,
make it in.
yeah, you may be aware that our students are visiting you during their final year projects. So
Yeah,
we should thank you for that also. And all people are telling, our students are telling that your cooperation is unmatchable. So we, on behalf of Meenakshi Sundararajan Engineering College Department of Mechanical Engineering, thank you very much. So
yeah, 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 yeah.
kindly entertain our participants also, whatever the question they ask, kindly inform whatever the things you wanted to disclose with them. Thank you very much, sir. Thank you.
Yeah. I'm quite thankful. Quite thankful that you yourself reached me using emails and try to invite me for this international webinar. So it's quite good to link with your engineering college. Good to know what type of condition or facility that you have inside the college. Your student in engineering college, I think one of top in India, perhaps. So we'll be looking forward to do some collaboration if you're interested.
Yes, sir.
Okay.
So this question is from Mr. Adarsh Rajashekar. His question
Okay.
is how to make coating that is able to cure underwater.
Okay. Probably I answer it in general because I'm not my background is not chemical. So probably I answer it in terms of mechanical background. So underwater itself, perhaps we can do that, but we can't go deep underwater. We can't really go deep underwater because the liquid gas interface itself it depends on the pressure difference. Pressure difference in terms what we have is that the liquid pressure and also the gas pressure inside the cavity. So let's say that the liquid pressure is quite high, so it will just penetrate inside the cavity. But probably in the future, probably in the future. Hope this one answer your question or your doubts.
Thank you, sir. One more question from Adarsh. How will you measure the coating layer thickness under the water?
Okay. Okay. So the coating thickness for my research is not that significant. For my research is not that significant. Because what I explore in my study, mainly my study is about the computational. So the coating one, as long as it can form the liquid gas interface, is good enough for my case. For the coating thickness itself, I think you have to spray it in a greater amount. So if you spray in a greater amount, then you last longer as compared if you put the coating just lightly. So you just disappear probably in a short period. So if you have that one, but you have to do that quite frequently if you want to maintain the hydrophobics. Okay.
Yes, sir.
I also
The,
hope that answered the question.
yeah.
Okay.
The next question is like from Niranjan. Does the hydrophobic coating wear off through time?
Yes, the
Does the hydrophobic coating wear off through time? The hydrophobic coating, will it wear off through time on after some time?
okay. In practical, yes. In practical, yes, because it depends on the condition. How long the coating will last, it depends on condition. Because in internal flow, it's much more okay. For external flow, what we have is that in the outside environment, what we have dirt, we have foreign things on the surface. So when we have those things, it will affect the coating. So probably it will last sometimes it will last month, sometimes it will last week. So it depends on the condition. So external condition, what we have that kind of thing. So it will wear off, but depend on time. For internal flow, it's much more better because we don't expose to the outside environment. Okay.
Yes, sir. Thank you. So the question is from Hariharan. Can the super hydrophobic coating be used in ships?
Until now, I haven't seen that be applied on ship or airplanes. What we usually apply is only daily basis, like apply on clothes, apply on car, apply on other surfaces, probably apply on industry application. Now, currently, what I do is that I try to apply on mixing flow. So flow A and flow B have to mix. So I did some superhydrophobic surface. So we'll see the mixing performance. One of the application. Other application maybe we can explore it. Okay.
Yes, sir. So one more question. Does capillary pressure influence the super hydrophobicity?
The hydrophobic surface actually influence the capillary. The hydrophobic surface actually influence the capillary.
Okay.
I can't recall how the influences, but you influence the capillary so that when you pump it, if the pipe or the tube is quite narrow, you'll have some additional pumping power needed just to pump it through. Once you pump it through, then you won't have that capillary problems. But capillary will influence the superhydrophobic. I maybe there is, but very small. I think. Okay.
Yes, sir. Thank you very much. I hope all the participants got their answers for the question. Uh, so once again, thank you, sir.
Okay. Sure.
Thank you
Sure.
for your
So
on behalf of our management and staff of Department of Mechanical Engineering, Meenakshi Sundarajan Engineering College. I I also thank our Secretary Madam Dr. K.S. Babai for giving us this opportunity to organize the webinar with University Sands Malaysia, Professor Dr. Yu Kok Hawa. I thank our HOD Dr. K. Balasubramaniam sir for being supportive in conducting the webinar. Finally, I thank all the participants for their kind cooperation throughout the session. Thank you, sir.
yeah, thanks a lot. Okay.
Yes,
So
yes, sir.
so
Thank you, sir. Yuko, sir. Your
yeah,
presentation
yeah,
was very informative, and it was very useful to our students and the research scholars. As a faculties, it is very useful for us also. So thank you so much for accepting our invite in the short term, for spending your valuable time and informative knowledge to our students, faculties, and research scholars. Thank you, sir. Thank you once again. Some questions some students are posting in the chat box. Still, they are posting some questions. Is that
okay.
possible to have, sir? We can have the questions. Shall I read out, sir?
Yeah, yeah, yeah. If there's question or doubts,
Yes, sir. Yes, yes. Shall I read out, sir?
yeah, sure.
Yes, sir. One student, Naveen, he has asked that does the toothpaste make a surface super hydrophobic?
Mm-hmm.
Does the toothpaste make a surface super hydrophobic?
It's a two phase that make
Yes,
the
yes.
face to
He
be
is having the doubt whether the toothpaste is a super hydrophobic surface.
okay. Okay. So yeah, you actually need to have two different phase to actually to have the benefit of hydrophobic surface. That two phase itself is liquid and also the gas. You
Yes,
can't
yes.
have you can't have just a single phase. For example, that I say to you is that you just can't have airflow. You just can't have airflow inside there, also airflow. So the hydrophobic surface mainly are for the liquid, and the second phase is the the gas is in the gas phase. So actually you need to have that. Okay.
Okay.
I think that answered the questions.
Yes, sir. Yes, sir. One more question from Suraj. Some of the fabrics, when they are new, exhibit hydrophobic property to some extent, but after use, they lose the property. Why it happens?
Mm, yeah, it's quite true. So in terms of application of it, some of the problem is that how to maintain the longevity of the superhydrophobic or the hydrophobic coating. So the thing is that when we expose to outside or outdoor, so we have, because outside we have air that's not pure in terms that we have vapor, we have dirt, we have other things. So that will stick on the surface itself, and it create the hydrophobic coating. So that's why that it won't last long. How long is it? Probably it's 1 week, 2 weeks, 1 month. So how to apply on this part is that you have to frequently apply the coating. That one is for the outdoor activities. For indoor activities, when not really exposed to this environment, much more longer. Okay.
Okay,
So
okay.
okay.
Only two more questions, sir. Only two more questions we have. Is there any way to make polymer hydrophobic? This question from Aravind CR.
Uh, Probably there's some research group that is looking on that. So they have a material. So we try they try to do it to have it as hydrophobic, but I don't really follow the progress itself. So probably if you are interested and no one did that before, probably you will be the first one. So probably on that part, uh, I haven't seen on that technology before. So probably you can try. Okay.
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 Then I request the participants to fill the feedback form. The link has been posted in the chat box. I request the participants to fill the feedback form. So e-certificates will be sent to the participants according to the feedbacks submitted, then according to the attendance those who have participated in the session. One more last question, sir. This is the last question. Shall
Okay.
we use these hydrophobic coating where the conduit surface damage due to friction between water molecules? Once again, I will repeat, sir. Shall we use these hydrophobic coating where the conduit surface damage due to friction between water molecules?
Okay. Okay. So meaning to say that what we want to say is that the hydrophobic coating will damage the water molecule, something like that.
Ah, yes,
Uh,
sir. Yes, where the conduit surface damages due to friction. So these hydrophobic surface can be used as a coating for the conduit surface to damage, which can which can be damaged with the help of maybe by the friction. So the guy
Probably
is saying that hydrophobic coating can be used for this conduit surface, whether it is possible to avoid friction damage.
probably probably to damage the water molecules is not that much. What we are mostly concerned is that the purity of water. Purity of water is that when the coating itself will mix inside the liquid, but sometimes very small amount, so the impurity itself is not that significant to affect anything. Even probably for health is also quite minimal. To break the water molecule itself is not really, in my perspective, it's not really significant. I think so. Not but that one I have to go and explore more. But from my perspective, it's not. So I hope that that really answered the questions. Okay.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Thank you, sir. Thank you once again, sir. Thank you for your valuable time, sir, for spending with us. Even though it's in Malaysia, it's almost 7 p.m. Thank you, sir, for spending this evening with us by your valuable knowledge. We will
Okay.
invite you for our international conference, which we are going to organize in our department, sir,
Okay.
so
So
that you can visit India if this pandemic situation is over.
okay, sure.
Yes.
I also look forward to join the platform or join the activities or the event organized by your college. And to be honest, I haven't been to India before. Probably this one will be the first if everything permit. So I quite thankful for your college that provide this platform to me. First time I engaged with Indian student through online. I haven't did that before, so this one will be my first time. So probably in the future or in the near future, we can engage in other platform or other event. So thank you again, just to bear with me for almost 2 hours. So just to listen me what I have to tell about superhydrophobics. I hope that interests your make you to have a greater interest in engineering. So if you want to contact me, you can contact me using emails. Frequently I'll reply emails. So I hope to see you all again. Thank you to Prof. Bala Subramanian again, just to create this platform. Thank you.
Yes, sir. To participants, please fill the feedback form which is posted in the chat box. I request the participants to fill the feedback form. Those who are in YouTube live stream, I have posted the feedback form in the YouTube live stream also.
Thank you, sir.
Now it's time to thank our management, Dr. K.S. Babai ma'am, who has granted permission to have our international webinar session. I thank our HOD, Dr. K. Balasubramaniam, for supporting us to organize this international session. I thank our principal, Dr. P.K. Suresh. I thank our Dean Academics, Dr. K. Umarani ma'am. I thank Toral ma'am. I thank our colleague K. Sridhar for the online for technical support for this organizing this webinar. Thank you all. Thank you. Participants, you can post your feedbacks in the link which is provided. I'm sure our students and faculties and research scholars has gained much knowledge about superhydrophobic surface, which is new. So we can think when we are getting in our day-to-day life, what are the superhydrophobic surface we are coming across. Thank you, sir, for giving this knowledge. Thank you once again, sir.
Okay. Okay.
Okay. Okay.
Thank you.
Yes, sir. Shall we end this session, sir?
Yeah.
Thank you, sir.
Thank you, sir.
See you all. Okay.
Yes, sir. Yes. Thank you, sir.
Yeah. Sure. Thanks.
Yes.
Thanks for the arrangement.
Shall I end this session, sir?
Yeah.
Thank you.
Thank you.
Feedback வாங்குது